Okay, so this is the last of the radiation modules. This time we're going to look at solving for temperatures and heat flows in radiation enclosures. So this will be radiation enclosures. Part 2, or say radiation enclosures continued. So last time we devoted most of the module to talk about view factors, but it didn't, and view factors are very important in determining how to solve radiation enclosures, but really what we're doing here is focusing more on the actual solution method itself, using the view factors. So here we go. So the question is then, what dictates heat flow from a surface I to go to a surface J? So again, think of an enclosure as having a number of surfaces. So we have n surfaces. So this is 1, 2, so forth, all the way around, and then we end up with surface n. So what dictates that heat flow? Well, there's really two things. The first thing here is the view factors. And the view factors, again, they tell you how much heat leaving I goes to J. And so that's one element of it, but the second element of it is the surface properties of each of the surfaces. And so what we're going to do, and I'm going to forego a lot of the math, but there's textbooks out there, especially at the graduate level, where they get into the details of where all this comes from. But the idea is that you can set up what's called a radiation resistor network that incorporates these two features here. So with the view factors, we have something called a spatial resistance. And simply put, you have a value R spatial, and we'll say Ij is equal to 1 over AI Fij, or using the reciprocity relation, 1 over AJ Fji. Right. And then on the surface property side, there's a surface resistance. And this is going to be for each surface inside the network. So say R surface I is 1 minus epsilon I over epsilon I AI. Right. So again, what we have here is we assume, and regarding the surfaces here, is that we're assuming, I'll make this different color, we'll assume that all surfaces are diffuse. Recall that diffuse means that the intensity is the same in all directions. Gray, which means that you have a value of a surface property, say emissivity, epsilon, that is independent of wavelength. And then one that I'll throw in there that I thought was it should be pretty clear, but just to make it official, is opaque. In other words, there's no transmission through the surface. It's an opaque surface. It only reflects or is absorbed. So if you look at an example here to show you what these resistance networks look like, is say there you have 3 surfaces. So 1, 2, and then we'll make this one curved for 3. All right. Now for each surface, there's going to be a heat flow. So we have a Q1, there's a Q3, and a Q2. And the surface has its own properties. T1, A1, epsilon 1 for that, T3, A3, and epsilon 3. And here is going to be T2, A2, epsilon 2. So the general idea for these types of problems is that you're provided with all the values of A's and epsilons, and you're provided with some values of T's and some values of Q's. So we can say, so for each surface, you're provided with the values of A, epsilon, and one of T and Q, and you're going to solve for the other of T and Q, right? So say, for example, you're provided with T1, but you're not provided with T2 or T3, then what you're going to do is solve for Q1, and then the temperature is at T2 and T3. But you're provided with, assuming you're given Q2 and Q3. All right, so let's show you how this radiation resistor network diagram all maps out for this particular example here. So the way it works is you start with a node that corresponds to the surface, and this will be your black body emissive power. So in other words, EB1, which we know from the past lectures is equal to sigma T1 to the fourth. And into this node is Q1. So the first resistance you see is the surface resistance for 1. And that leads you to the radiosity J1. And if you continue on, you know the radiation that leaves surface 1 can either go to 2 or 3. So we're going to have a spatial resistance from 1 to 2. And we'll have a spatial resistance from 1 to 3. So that radiation then has a value of J tied to it on the node after it ends that spatial resistance or achieves that spatial resistance. So likewise, you can have a resistor here that'll be the spatial resistance from 2 to 3 or 3 to 2. It's, with the reciprocity rule, you can do that. And then you finally finish with the nodes for 2 and 3. So here will be the surface resistance for 3 to EB3, and the surface resistance for 2, which gets you to EB2. And then you do have the heat flows coming in as well, so Q2 and Q3. So what this is a visual representation of a system of equations that you have to solve. And under certain special circumstances, you don't have to set up and solve a system of equations. Normally, you would do it with solving like an AX equals B type, linear system solve. But under a few special conditions, you can reduce it down to the network down, so you can solve for the unknowns. So let me show you a couple of examples here on that. But before we do that, I just want to point out here that in general, if you look at the expressions here, if you look at surface 1 with R surf 1, you can see that you set it up as Q1 equals EB1 minus J1 over R surf 1. And if you look at the units of these, I should start with the enumerators. So both EB1, the black body emissive power, and the radiosity both are heat fluxes. So we'll say this is watt per square meter. And the resistances, if you go up here, the surface resistance, the emissivity is dimensionless. So your end up is 1 over A. So it's just going to be 1 over meter squared. So what you get is watts, which is good. This is what we expect because we're dealing with a heat flow. Also, to make sure that the units are consistent for the different resistances, you see that you have 1 over A IFIJ or 1 over AJFJI. The view factor is dimensionless, so you have 1 over area again, so 1 over meter squared. So this all works out pretty well. So in general, what you have are it's a fancy way of solving a system of equations where you have this equation here, and then you can also define heat flows between, say, 1 and 2. So if we say Q12, where Q12 is defined as that portion of heat flow that goes between 1 and 2, you can see here that this is going to be equal to J1 minus J2 over our spatial 1, 2. So you set up and solve a system of these equations altogether. All this is mathematically derivable fairly easily if you look in a textbook and learn where it comes from. But we're not going to worry about those details here. I'm going to show you the types of problems you need to know for purposes of doing well on the qualifying exam. So we'll focus on that. All right, so let's talk about a few examples here. So first example is the roof of a building at night. So say, for example, there's a surface, here's our roof, and the roof does allow for heat to pass through. So we have, we're providing Q1 into the roof. So here's, we'll call this surface 1, and then you have the night sky above it. And this night sky is, we'll call this surface 2. And what we're going to say is that way back when we were talking about black bodies, we said the night sky, clear sky, outer space is basically kind of like a black body because it has such a huge depth to it. We'll say the emissivity is roughly equal to 1. So it's like a black body. So we're getting clear night sky. And then the roof itself, we'll give it some values here. We have some, non-zero, but not equal to 1 value of epsilon 1. And then we have some T1 associated with this. And in the night sky, you're given a value of T2, which, by the way, is somewhere, I'll say roughly equal to 0 Kelvin, but it's really like 2 to 4 Kelvin is the more realistic temperature of outer space. So what we're trying to find then is what is the heat flux that goes from 1 to 2? So let's try to figure this out. So we take our resistor diagram method here. We say Q1's coming in. We have a node EB1. There's a surface resistance at 1. There's only 2 surfaces, so when this reaches J1, the next resistor goes to J2, which would be the R spatial 1, 2. Then you have the surface resistance at 2, which gets you to EB2. And then there's a Q2 over here. All right, well, let's simplify this out. So the idea here first is that since you have Q1 coming in on the left and Q2 on the right, the idea is that the energy all has to balance out. I didn't mention this, but this is all steady state. So as a result, Q2 must equal to minus Q1. In other words, we have a Q1 coming into the resistor network on the left. There has to be a Q1 leaving on the right. So we have Q2 equals minus Q1. All right, our surface 1 we can plug in as 1 minus epsilon 1 over epsilon 1 A1. Our spatial 1, 2 is 1 over A1 F1, 2, and our surface 2 is 1 minus epsilon 2 over epsilon 2 A2. Okay, so epsilon 2 is equal to 1. So if we put a value of 1 in here, the whole thing then goes to 0. That's fine enough. And then F1, 2, just by observation, all the heat that's leaving surface 1 has to hit surface 2 because surface 1 is flat. Surface 2 covers over surface 1. So here we have a value of 1 for this. So the whole thing altogether is equal to 1 over A1. So if we were to combine these 3 resistors in series, we can say R total is equal to 1 minus epsilon 1 over epsilon 1 A1 plus 1 over A1, which means that when we use a common denominator, we have 1 minus epsilon 1 plus epsilon 1 all over epsilon 1 A1. The epsilons cancel out. And so what we get is 1 over epsilon 1 A1. Okay, so if we look at the endpoints here, we could say then that Q1 is equal to EB1 minus EB2 over R total. Recall that EB1 is sigma T1 to the fourth. EB2 is sigma T2 to the fourth over R total, which will be 1 over epsilon 1 A1, or you get a value then of epsilon 1 A1 sigma T1 to the fourth minus T2 to the fourth. We can define the heat flux Q, go back up here, Q12 with the double prime for to represent heat flux. That Q12 double prime is simply going to be the amount of heat of leaving 1 going to 2, which is all of it, divided by A1. So in the end, what we get is epsilon 1 sigma T1 to the fourth minus T2 to the fourth. So this is the kind of the first relation that we see when we talk about radiation and undergraduate heat transfer. And so they call this, okay, this is the Stefan Boltzmann law. You can see there's some subtleties that are mixed in. For example, this works when you have two surfaces where one has a value of epsilon 1 that's declared, and then the other surface is a black body that represents the surroundings. So if you have surroundings that for whatever reason are not a black body, then you can't use this relation that we've derived here. You have to use a different one. So what this does, I like this as an intro example, because what it does is it kind of shows where that relation comes from in the context of using a resistor network. All right, so let's talk about a second example, getting it slightly more complicated here. So the second example is a radiation shield. Okay, so here we're going to have three surfaces. So you have surface 1 and 2, and these go off into infinity, in and out of the page and up and down. So here's surface 1, and there's a value of Q1 going into this. And surface 1 has T1, value of epsilon 1 and A. Where A is a very large value. Over here is surface 2. Same deal, you have a T2, epsilon 2, and A. And then there's a Q2 coming in here, which again is just going to be minus Q1. Great. So what makes this interesting is we're going to stick in the middle a radiation shield. So think of this as a thin material that's being placed in the middle to block radiation going from 1 to 2. So here's our shield. And the shield has some emissivity epsilon sub s, but also has a temperature Ts, and it also has an area A, just like surface 1 and 2. So what the radiation shield does here is we're going to say that epsilon 1 and epsilon 2 and epsilon s all have the same emissivity. We'll call it epsilon. But what we're trying to find is what are the influence of the shield. So we say, what is the ratio of Q shield over Q if you take the shield away? Okay, so Q shield is if you include the shield in the network, and Q no shield is when you take it away. So let's start with Q no shield. For that network, all you have is surface 1 and 2. So Q1 comes in, you have an EB1. Again, we have a surface resistance. Get you to J1. Spatial resistance that goes from 1 to 2. Then you have the radiosity for 2, and then finally a surface resistance at 2. Get you to EB2. So let's look at each of these values here. And notice that if I let's just say, for sake of argument, to make things simpler, is say all of the emissivities are 1/2. It's kind of a convenient number to use here. If you do that, R surface 1 is 1 minus epsilon over epsilon A, right? So 1 minus epsilon is 1/2 divided by 1/2, the answer is 1. So this ends up just being 1 over A. Our spatial 1, 2 is 1 over A1 F12. Again, F12 is equal to 1. All the radiation leaving surface 1 has to hit surface 2. So then what you get combined then is 1 over A. R surface 2, just like R surface 1, is also going to be 1 over A. So R total is equal to 3 over A in this case. Let's look at it if you have a shield. Well, in our case here, we have Q1, we have EV1, surface resistance, which is J1. Now, all that radiation leaving 1 now hits the shield on the left side. So to account for that, we're going to say R spatial 1, and then we'll say shield on the left. So this will give you the radiosity on the left side of the shield. So such as we see there. And then we have the surface resistance of the shield on the left side, which gets us then to EB shield. We'll assume that the shield is very, very thin and that the whole shield is at a uniform temperature. So now you have the R spatial resistance from the shield on the right going to 2, and that gets you to, oh, sorry, I messed up. We have the surface resistance on the right side of the shield. Shield right, which gets you to J, shield right. Then you have the spatial resistance from the shield on the right going to 2, which gets you to J2. And then this gets you to EB2 when you have the surface resistance at surface 2. And just like if you look up at what we had for the no shield case, all of these are 1 over A. Right. So the R total then is going to be 6 over A if you just count them up, all in series here. So R total is now 6 over A. So Q shield over Q no shield is going to be EB1 minus EB2 over R total shield. We're going to divide all of that times or by EB1 minus EB2 over R total no shield. So you can see that it's simply going to be the ratio of R no shield over R shield. R no shield we found out was 3 over A, and R with the shield is 6 over A. So the value is now 1/2. So it's a kind of a quick, straightforward calculation to show you that when you insert a shield between two surfaces, like on a gap between two surfaces, you can cut the heat transfer by half in our example here. In reality, you can get much better performance than that. It shows us the value of emissivity of 1/2 for convenience sake. But you can see these shields being used. I've seen them used in attics, attic spaces, so that it allows, it prevents the heat from the inside part of the roof, making its way through the attic down to the living spaces below. And so they're effective and they're a great way to mitigate heat transfer. So then I have one more example, which is the most complex of the three. And this is the re-radiating surface. In an enclosure. Okay, so say we have a triangular surface or a triangular domain here. So we'll make an equilateral triangle, and this is our cross section. And we'll say that there's a surface 1, which again has our typical stuff here, Q1, epsilon 1, A1, T1. We'll say this is surface 2, Q2, epsilon 2, T2, A2, and surface 3, Q3, epsilon 3, A3, T3. All right, so you've got a little bit of all of that going on. And so in our particular example here, let's say that we're given T1 is 1,000 Kelvin, T2 is 500 Kelvin, epsilon 1 is 0.8, epsilon 2 is 0.4, and epsilon 3 is 0.7. So the key here, and it should, oh, before I jump into the big key here, to say A1, A2, and A3 are all equal to 1 square meter for simplicity. So here's the key. We'll say surface 3 is re-radiating. So what does that mean? Is that it's insulated. So that means essentially that Q3 is equal to 0. So in other words, you can think of a surface 3 as having some insulation behind it. So we'll just put some hash marks here. All right, so there's no heat coming in the surface 3. Everything that comes in is basically bounced back out, either through emission or reflection. So the idea behind this is that now when you draw a resistor network diagram for this system, which is going to be the same as what I had drawn way back up here, except I'm going to simplify it, you can have it where all the heat that leaves 1 must make its way to 2, since 1 is a higher temperature than 2. So here's what we're going to do. We're going to find 3 things. For surface 1 and 2, we're given temperatures 1, temperature 2, so we're going to find Q1 and Q2. Since surface 3, we're given a value of Q, we're going to solve for T3. And I'll show you how we can do that with our resistor network diagram. Okay, so we'll redraw this again. Q1 goes into EB1. Our surface 1, we get to J1 here. We have a spatial resistance 1 to 2, which gets us to J2. And we have our surface resistance at 2, so it gets us to EB2. We also have surface 3, we have a J3 with a spatial resistance 1, 3. And we have a spatial resistance 2, 3. And then there's an EB3 with a Q3. And this is going to be our surface 3. Okay. So we can write down what these are. Let's go ahead and just, we know the equations for the surface and spatial resistances, so we can solve it out. R surf 1 is 1 minus epsilon 1 over epsilon 1 A1. You plug in the numbers, is 0.25 inverse meter squared. R surf 2, using a similar equation, you get 1.5 inverse meter squared. R surf 3 is going to be 0.42 inverse meter squared. Our spatial 1, 2, maybe before we need the view factors for that. So if we back up, this is an equilateral triangle. So just by observation, we know that, say, for example, the view factor 1, 1 is equal to view factor. We've got a view factor 2, 2. There's a view factor 3, 3 is all equal to 0, right? Because we're flat surfaces. Note that it's difficult to use, to use it when you have complicated view factors. To use the resistor network, for example, if you have, or notice that the resistor network doesn't include where you have surfaces radiating back on themselves. So all of the examples we've had F11, F22 being 0. Say, but by observation, all the heat leaving 1 must go between 2 and 3, and since it's an equilateral triangle, half by symmetry, half is going to 2, half is going to 3. So we say F12 equals F13 equals F23. It's going to be 1/2. So our spatial 1, 2 is 1 over A1 F12. You know, F12 is 1/2. And since A1 is 1 square meter, this is just going to get you then 2 inverse square meters. And this is going to be the same then as R spatial 1, 3 and R spatial 2, 3. All right, so continuing on, we can plug some of these numbers in. So maybe we can fill them in right now. So R surface 1 is 0.25. And we'll just imply that we know it's inverse square meter. This will be 2, 2, 2. R surface 3 is 0.42. And this is 1.5. Okay. Now, the big thing here is that since we're given Q3 is equal to 0, we see that if Q3 is equal to 0, that means that there's no heat flow between EB3 and J3. So the R surface 3 doesn't even matter. So we see then that EB3 must equal J3. So we can simplify this as EB3. Another thing we can see then is that since Q3 is 0, we have the same situation before that. Q2 then, which is going to be right here, is going to be minus Q1. In other words, all the heat that's coming in from 1 going to 2 is going to be absorbed by 2. So Q2 equals minus Q1, just by doing an energy balance on the whole resistor network here. Okay. So what we can do then effectively is we can simplify this into a resistor network that looks, and again, we'll make it a simpler looking resistor network, but we'll capture all the important features for purposes of what we're trying to do here. So Q1 then goes into EB1. We have resistance at 0.25. Then it hits J1. Spatial resistance of 2. Another one of 2. Another one of 2. And that gets us down to J2. The value of 1.5, which gets us to EB2. Right? Because the idea is that there is no heat flow going in this part of the branch up here. So simply we can get rid of that whole branch altogether. And so we're left with this. So now it becomes just an exercise in doing circuit simplification. So now there's a Q1. Again, 0.25, 2. Now we can combine these two series resistors in series. This is now 4. 1.5 to get you to EB2. We can provide or examine the series and the resistors in series, or in parallel rather. So we'll say 1 over R, and we'll say this is our parallel, or maybe we'll say P for parallel, is going to be 1/2 plus 1/4, which is going to be 3/4. So our parallel is equal to 4/3. Again, units in all this is inverse meter squared. So our resistor diagram now looks like Q1 EB1, 0.25, 4/3, and 1.5 to EB2. And now you just simply add them all up to get your total resistance. So the last one we have is Q1, which goes into EB1. Then we have EB2, and the equivalent resistance here. I can find my notes on this. Is 3.083, if I did the math right. So now we can solve it out for that heat flow from Q1. So Q1 is going to be EB1 minus EB2 over R total. So sigma T1 to the fourth minus T2 to the fourth, all over 3.083 inverse meters squared. And again, T1, we can plug in 1,000. And T2 is 500 Kelvin. So we get our result. And that result ends up being, once you can divide by 1,000, turn it into kilowatts, you get 36.9 kilowatts. And again, this is equal to minus Q2. Okay, so we have what Q1 is. But then the other thing we want to find, and we have Q2 as well. Q2 is minus 36.9 kilowatts. Great. But then the other thing we need to find is what's the temperature associated with surface 3? We know that all the heat coming in has to leave. That's where we're at here. So if I go up here to this diagram, we can say that we can divide up Q1 into two parts. This is going to be Q1, 2. And then we'll say Q1, 3 is doing this. All right, or if you want to go to the diagram here on the right, Q1, 3 is up on top and Q1, 2 is on the bottom. So let's take a look at this a little bit more closely here. We're going to draw that diagram again. Well, first off, we want to find what J1 and J2 are. That'd be useful. So J1 is going to be EB1 minus Q1 times R surface 1, using our standard electrical resistance analogy here. So EB1 is the voltage here, then we have J1 is the one next to it, then R surface 1's in the middle, R surface 1's between the two. You plug them in, and what you get is a value of 1.09 times 10 to the 5th watts per square meter. J2 is going to be EB2, but now we're going to add Q1 because it's upstream in the network, R surface 2. And the value we get there is 5.89, which is 10 to the 4th watts per square meter. So if we, again, look at J1 and J2, we have J1 is here, Q1 is going into it. We have a value of 2 down here to get to J2, and then we have the value of 4 up here. And again, this bottom part is Q1, 2, and the top part is Q1, 3, we'll say. So by looking at the J1 minus J2, in other words, the voltage drop across the whole thing, we can look at it as an equivalent, as Q1 times R parallel. We can also look at it as Q1, 3 times 4, right? Or whatever that value is up top. So Q1, 3 is equal to Q1 times R parallel over 4, right? And R parallel being 4/3, which we found out before. So from that, we can get our value of Q13. And our value of Q13 ends up being 12.3 kilowatts. And since we have that, we can then determine EB3. EB3 then, we go way back to our diagram right here. EB3 is the value associated again. Remember that EB3 equals J3 because of there's no heat going through that network or part of the network there. So EB3 is J3, so it's on the top here. So it's going to be Q13 times the spatial resistance of 2. So it'll be J1 minus R spatial 13, which is 2, times Q13. So again, this value here is going to be 2. And that gives us then a value of EB3. And then finally, we say that T3 is equal to EB3 over sigma, all to the 1/4 power. Okay, so actually I went back through, I had paused it for a moment here to look at some of these numbers. I think I made some math mistakes in the earlier part of my example, so I'm going to go correct them now. So if you're following along and maybe wondering about why you're not getting the same answers I am, I can help you out here. It's all on my end here. So Q1, it turns out the value is going to be 16.3 kilowatts. The value of J1 and J2 are going to be a little bit different. Hear that. All right, so J1 ends up being 4.99 times 10 to the 4th. And J2 is going to be 2.90 times 10 to the 4th. As a result, Q13 is 5.43 kilowatts. And then when you do the math here, you get a value of T3 being 910 Kelvin. So the thing that kind of tipped me off was I was looking at my answer and it was actually above the value of T1 of 1,000 Kelvin. So I knew something was wrong here. So I went back and checked my math and I was able to find the error. So that's essentially how I use a rewriting surface. Now there's a couple things, final tips I want to give you on this that are important to know. So number one is you cannot combine radiation and conduction / convection. Resistance networks. All right, what I mean by that is that the value for example, surface and spatial units are going to be meters to the -2. If you look at, for example, in conduction units, you have L over Ka. The units there tend to be Kelvin per watt, right? So different units, you cannot mix them. That will not go well. Though, of course, the exception to that is if you use a radiative heat transfer coefficient equivalent, then you have 1 over HA, which then gets you, Kelvin per watt. You're going to go about that route. The second thing, which is a little more subtle, is specific to what we're talking about here, is you may get a situation where that you have surface 3 being a black body. So if surface 3 is a black body, in other words, epsilon 3 is 0, that means that our surface 3 is equal to 0. Actually, black body means it's equal to 1, sorry. Our surface 3 is 0. Notice that we have R surface 3 being 0, or effectively you have E sub B equal J3 here. You have the same effect. EP3 is still equal to J3 if R surface 3 is 0. The difference, though, is that Q3 is not going to be 0, or not necessarily 0 in that case. So you cannot assume it's the same strategy as a re-radiating surface. So you can say here that not a re-radiating surface since Q3 is not equal to 0. So again, if the R surface 3 is 0, we have EB3 equals J3 like a re-radiating surface, like in the example. But it turns out it will affect your results if you're incorrect and you treat it like a re-radiating surface when it's actually not. So sorry for the little mix-up with the numbers, but hopefully this is clear. That concludes all the stuff you need to know for radiation for the qualifying exam.